Hello friends, so one second. Yeah, so it's working now. So today we are going to discuss three questions, and these three questions are from the rotational motion. And the first question so in the first question we are given two identical wheels, each with moment of inertia I, are connected by a massless horizontal axle of length L, as shown in the figure. The system rests on a perfectly frictionless horizontal surface. Each wheel spins about the axle with the angular velocity omega, and simultaneously the entire axle wheel assembly rotates about a vertical axis, passing through the midpoint of axle with the angular velocity of capital omega. Determine the maximum value of this capital omega for which both wheels remains in contact with the ground. So in contact with the ground is from, we can say we are mainly interested in finding out the value of the normal, or we can say when the value of normal is equal to 0, the contact with the ground will be lost. So we are going to use that particular condition. And the basic figure, we can just draw it, and we are having two wheels. This is the first one and the second one, and they are connected with the help of a axle, and both wheels are on the same level, and it is given that they are rotating with their axis passing through the center with the angular velocity of omega, and along with that they are also rotating with an axis which passes through the center of the axle with the velocity of capital omega, and the total length is given to us of this axle is L. And so the various forces that will be acting on it, first one, there will be rather two forces. One will be our normal, so let us call this as normal on the left, and we have our normal on the right, and also we are going to have our weight mg in the downward direction. Okay. And we are given that they are having a moment of inertia of I, and so let us assume that the center, this is our origin, so to the left of it, it will be minus L by 2, and to the right will be plus L by 2. Okay, we have taken this center as our origin, and we can also say that each wheel is having a mass of m. Therefore, we can write that the angular momentum of our each wheel, so we can say the angular momentum of each wheel, let us suppose that is our L, and that will be equal to I times omega. I is the moment of inertia and omega is its angular velocity. So first of all, we are going to find out our rate of change of angular momentum. Okay, and because we already know value of L and we know the capital value of this omega, therefore we can write that, so we can say that our axle is rotated about the vertical at omega, and each spinning wheel angular momentum is our L. Therefore, from here we can write that rate of change of wheel's angular momentum, rate of change of wheel's angular momentum, and we can write this as our dl upon dt, or we can write this as our L single derivative will be equal to omega times our L. And we can find out the magnitude of the torque that is being produced by each wheel. So we can say that torque due to each wheel, let us call this as a tau W, then this tau W will be equal to our omega times L. And we already know value of L, so we can write this as our capital omega times I and angular velocity omega. And the torque, we have two wheels and both will be producing the same torque and in the same direction. Therefore, we can say that our total torque let us call this our tau, or we can say our tau t, will be equal to twice omega I times omega. And we have two contact forces. One is our normal on the left side and other one is the normal on the right side. Okay. So therefore, the torque will be also generated because of these two normals. So we can say that the contact torque, because both are contact forces, so we can write the contact torque about the axis center, and let us call this a tau c and this tau c will be equal to our, because of our left, because of our right, and multiply by the lever arm, that is L by 2. And under equilibrium condition, or we can say for equilibrium, our total torque should be equal to torque due to the contact. So we can replace respectively. So this comes as 2 omega I times omega is equal to left minus right, and we have our L by 2. And we can also write the equation for our vertical, but there is no as such motion in the vertical, so we can just ignore them. And if you want to write, we can simply put that for vertical, we have two forces, left plus right will be equal to the weight twice mg. Okay, and this is not required, so we will keep this aside. And in this case, we have to find out, or rather we can say, as this value of omega, that is with respect to the central axis, is going to increase, the difference between this L normals is also going to increase. Okay. So it means at certain point of time, the one of the wheel is going to lose the contact. Okay, and we can just assume that, let us suppose the right wheel loses the contact. Okay. So we can say, let right wheel loses the contact. So obviously the normal of our right wheel will be equal to 0, and the normal of the right wheel is equal to 0, so we can substitute in this equation, and we get this as twice omega I times omega is equal to normal of our left and our L by 2. Okay. And we can use this vertical equation, substitute value of normal to the right as 0, so we get our normal to the left is equal to twice mg. This is the only significance of this particular equation. So we substitute here, and we get this over twice mg L by 2. Okay. And for this we can substitute the value of this omega. We can write this as omega max. Okay, because a certain value of this omega max, one of the normal will be equal to 0. And here with this 2 cancel out with 2, therefore we get that value of the maximum value of the omega will be equal to, this is our mgl divided by 2I omega. And if we require, we can substitute value of I and as well as whatever things we require. Okay. So this is the maximum value of omega, and for which the wheels are still in the contact with the ground. Okay. So this is the first question, and we come to the second question. And the second question, it states that, consider a lollipop made of a solid sphere of mass m and radius r, radially pierced by a massless stick. The free end of the stick is pivoted at a point on the frictionless horizontal surface, see figure. The sphere slides along the ground while maintaining the same point of contact, and its center moves in a circle of radius r with the angular speed of capital omega. Show that the normal force between the ground and the sphere, that is our f of n, is equal to mg plus mr omega square, which is independent of r. So this is the basic question given to us, and here we can draw the figure. And so we are having a, suppose this is the solid sphere, and this is our ground and its center, and it is connected with a stick. So this is a stick, and we are given that our r is small r is the radius of the stick, and the point of this stick up till this radius, this distance is given as capital R, and it is also rotating about this pivot point with a angular speed of over omega, and m is given as mass. So this is the basic figure given to us, and we can, you can say, draw the forces that will be acting on it. So first force will be obviously the weight mg, that will be acting in the downward direction. Stick is given as massless, and there will be also a tension that will be acting on it. Okay. So you can say the tension, let us suppose that is our T, is acting on the stick, and we can divide this T into two parts. So let us call this our T of x, and this we call as our T of y. Okay, so these are the various forces that will be acting on it. Okay, I forgot to mark the normal, so there will be also normal, and that is given as our f of n. Okay, that is given to us. Okay. So we can write the equation, and in the vertical motion, so you can say the vertical equation, we have our f of n, and this is minus T of y and minus of mg, and in the vertical direction there is no motion, so it will be equal to, or let me put this as, okay, we can directly equate it equal to 0 because there is no as such motion in the vertical direction. Okay. And furthermore, we can write this as okay, and there is a tension Tx, and this Tx will be providing the necessary, you can say, our centripetal force. Therefore, we can write our horizontal equation, and we can write this as our T of x will be equal to our mass and acceleration in radial direction. Okay. This horizontally is nothing but radial, and we can write this as our m and our omega square times r. And we can find out the ratio of this Tx as well as Ty, and therefore we can say that our Ty upon Tx will be equal to our small r upon capital R. This is quite mathematically, it's true. But our T of y is in downward direction, so we can just put it negative, or let us move the negative to the other side. And okay, let me write it. This is our minus of Ty, and therefore we can say that our T of y will be equal to minus r upon capital R and our T of x. And we can use this value of T of y and solve it further. One second. Okay, we can substitute value of T of x and solve it further. So we can say that our T of y will be equal to minus small upon capital R times T of x. T of x is our m omega square times r, and here our r and capital R cancels out, and this comes as our minus mr omega square. And now we can easily substitute this in our main equation. Let us suppose this is our equation number 1. So we can say from equation 1, we have our f of n okay. Okay, in this case we have to remember that because we have already considered the sign of minus T of y, so I am going to write this as our plus and this as minus T of y. It will be convenient to substitute the value. Therefore from equation 1 we get this as our f of n will be equal to plus minus, and we have mr omega square is equal to mg. Therefore we get our normal force is equal to our mg plus mr omega square. Okay, that was the required question. We have to find out our normal force. So now we come to our third question. So in this question it states that a massless axle has one end attached to a wheel modeled as a uniform disk of mass m and radius r, while the other end is pivoted on a frictionless point on the ground as the figure. The wheel rolls on the ground without slipping, with the axle inclined at an angle of theta above the horizontal. As the wheel rolls, the point of contact with the ground moves in a circle with the angular frequency of omega, capital omega rather. So in this case we have two parts, A and B, and it states that show that the angular velocity omega of the wheel points horizontally to the right at the instant shown, with the magnitude omega is equal to capital omega upon tan theta. And part B, show that the normal force between the ground and the wheel is represented by this particular equation. So this particular question looks a little bit tricky, but it is very convenient to solve it. So first of all, let me draw the figure. So in this case, we are given a wheel or disc, and its center is connected, or we can say pivoted, to a point, and this angle is given as theta, and the radius of the is given as r, and it is also rotating about the pivot point, and let us call this as point as O, and with the angular, that is our omega. So it means we are having two types of motion in this particular case. One will be that it will be moving the center of mass, or we can say pivot point. It will be moving with in a circular radius, and accordingly it will be also moving in the wheel will be spinning. So we have two types of motion, and one we can call it a spin motion, and let us call this as point as P, and let us call this as P prime, and this point is our P. So we can say there are two simultaneous motions. So the first one, let us call that a spin motion. And the spin motion is about our OP. Spin motion about OP. So it is spinning about this particular axis, which is our OP. And let us call, in this case, its angular speed as omega s. And its direction obviously will be in this direction. So this is our omega s. And the second one is that our center of mass motion about and let us call this as our Q. Okay. So center of motion about OQ, and it is already given that it is having a omega angular velocity. So therefore we can say that we can represent our this so let us so let me draw the so this is our point O, and we are having omega s, and we are having our omega, and so this is our angle theta, and this will be our omega. And we can easily find out the direction of this omega. So we can say that the direction of omega will be along OP prime, which is basically line joining line joining the point at rest. The line joining the points at rest. Okay, so it means we are having 2 points of rest at this particular moment where figure is drawn. One point of rest is our O, other point of rest is our P prime. So the omega is going to have in this direction. And so we can divide this omega s into 2 components, and one will be our omega s cos of theta, and other component will be our omega s sine of theta. Therefore, we can write that our omega is equal to omega s cos of theta, and omega is equal to omega s sine of theta. And if we divide these two equations, we can write this as our capital omega upon omega is equal to, we can write this as our omega s sine of theta, omega s cos of theta, and omega s is going to cancel out. So from here we get that the spin angular velocity, that is our omega, or one second, angular velocity omega will be equal to our capital omega divided by tangent of theta. So this was our part first. Okay. And now we come to our part B. And for part B, let me redraw the figure again. So this is our spinning wheel, our base, and it is connected to center. This angle is our theta, and it is moving with the angular velocity of omega. So in this case, let us define, and we are having, this is our omega s, and let us define our coordinate axis. So we are going to define that in this direction we are having x-axis, and this is our y-axis, and z is our out of the plane. So this is our z-axis, and I think I forgot to, so this length is given to us, this length is our L. So we have, and R is the radius and L is the length. So we can easily find out the relationship between L and R. So we can write that our L is equal to R tangent of theta, or we can say our tangent of theta is equal to R upon L. And we can find out the moment of inertia about the respective axis. Let us find out the moment of inertia about x-axis, and we call this as our I of x. Y-axis we call this as I of y, and z obviously it will be 0, but still we can put it equal to I of z. Therefore we can say that our moment of inertia about x-axis, that is our I of x, and it will be equal to over m r square upon 2. And we are going to find out now moment of inertia about y-axis. And in order to find out this moment of inertia, we are going to use theorem of parallel axis. And for the theorem of parallel axis, we know that the moment of inertia of this disk about its diameter, we already know this value, and we are required to find out the moment of inertia about this y-axis. So both are parallel with each other. Therefore, we can say that our moment of inertia about y-axis is our I of y, and that will be equal to moment of inertia about our, let us suppose we call this point as diameter. Okay, let me call this as q. So this is our p prime, and let us call this as our q. So we can say moment of inertia about the diameter and that diameter is qp prime plus the mass and the distance between the two axes, that is our L, which comes as L square. And simply substituting value of this moment of inertia about the diameter, therefore we get that our I of y will be equal to mr square upon 4 plus our m, and we already know that our relationship between our L and R, so we are going to use that. So we can say our L is equal to R tangent of theta. So we can write this as our R tangent of theta whole square. So these are the moment of inertia about the y-axis, and therefore we can say that the angular momentum of the entire system, angular momentum of the system, and let us call this as our L. So L will be equal to our angular momentum because of our x-axis, comma angular momentum of our y-axis, and for the z it is equal to 0. So this is our L of x, and this is our L of y, and last is our L of z. And we can simply substitute the value of I of x and omega of x. Therefore we get that our L is equal to I of x is our m r square upon 2, and omega of x is our omega cos of theta, and I of y we just calculated using the parallel axis theorem, this one. So we have our mr square upon 4 plus mr square upon tangent square theta, and omega of y is our omega sine of theta, and for z is equal to 0. And we can draw our L of x as well as L of y and find out what will be the direction of the resultant, our L. So we can say that our L of x is our along x-axis, and we get our L of y and the resultant will be equal to our L. So this will be somewhere here. And this, our L, we can divide this L into two components. So we are going to have our parallel component of L. So this will be our L parallel, and the other component will be our L perpendicular. So, okay, and we have our L of x. So this angle is our theta. So we can say in this direction we are going to have our Lx cos of theta, and this will be over Lx sine of theta. Okay. Similarly, we can write our L of y, and this angle will be over theta. So we are going to get this will be our L of y cos of theta, and this direction will be our Ly sine of theta. Therefore, from here we can write that our L parallel will be equal to Lx cos of theta plus Ly sine of theta. And we already know value of our Lx as well as Ly. So this is our Lx. So we substitute it. We get our L parallel will be equal to, we get this as our m square upon 2 omega, and cos theta will be giving us cos squared theta plus, and we have our L of y, and this is a big one, so we can write it here, m r square upon 4 and plus m r square upon tangent square theta, and this comes as our omega, and we have this is sine theta and sine theta, so it coming as sine square theta. And now we can easily calculate the torque. So from here we can say that our torque, which is nothing but our rate of change of our momentum, or we can write this as our L parallel and multiply by the angular, angular, but capital angular velocity with respect to the axis. Okay. So it is moving in this direction with omega. And now we simply substitute value of this L, or we can multiply the value of L parallel with our omega, and this will be giving us, we can also substitute value of this omega because we know the relationship. Okay, so let me write it here. So we get this as our mr square upon 2, and this omega is equal to omega upon tangent of theta. This we have already proved in our part A. So we can write this as our omega tangent of theta, and we get this as cos square theta, and multiply by omega, we get this as omega square, and that will be a plus, and we can just open the bracket and multiply it. Okay, that will be much more convenient. So we get this as our mr square upon 4, and here we are having this as omega upon tangent of theta, and multiply by sine square theta, and this is our omega square plus, and second part, we are left with this as our mr square tan square theta, and this comes as our omega upon tangent of theta, and we have this as sine square theta, and this comes as omega square. Okay, now it is only calculation are left. More or less, rest of the things are complete. So here we can take out from the entire equation, we can take out some things as common. So we can write this will be equal to our mr square omega square upon tangent of theta. And from the first part, only left is our cos square theta divided by 2 plus. From the second part, we are left with only our sine square theta divided by 4 plus. And from the last part, we are left with our sine square theta, and denominator will be our tangent square theta. So we can write this as our sine square theta upon cos square theta, and this sine square cancels out. So this comes as our cos square, and we can add this cos square into this cos square. Therefore we get this as our m r square omega square tangent of theta. So this will be 1 by 2 plus 1, that will be equal to our 3 by 2 cos square theta plus 1 by 4 sine square theta, and this is the value of our torque. But we are supposed to find out value of our normal. And okay, so we found out this torque with respect to our, that is our angular momentum, that is our L parallel. We can also calculate our torque with respect to the forces. There will be two forces acting on it. So we can say our torque due to forces, and there will be two forces. So let me redraw the figure, and so this angle is our theta. So one force will be our mg in the downward direction, and other one will be our normal in the upward direction. Okay, so these are the two forces acting on it, and the length is given to us is our L. So we have torque due to two forces. First is our torque due to our mg. So we can write this as our force mg and the perpendicular distance, and this perpendicular distance will be our L cos of theta. So this is mg and multiplied by L cos of theta. And we need to find out for the second part, and for that let me redraw this triangle again. So we know that this point is our P prime, this is our O, and this point is our P. Okay. Therefore we can, this is our my O P prime, and this point is our P, and I can join this our P and P prime. That will be nothing but our radius. So this is our radius and this is our length, angle theta, and this is our 90 degree. Okay. And the normal is somewhere here. Therefore, for normal, we can say this perpendicular distance, we can write this will be equal to our L upon cos of theta. Okay. and this is our radius. Therefore, we can say that the torque due to the normal will be equal to our force normal and the lever arm, that is L cos of theta. And we have two forces, both will be producing torque in opposite clockwise and counterclockwise. Therefore, we can write that our net torque, that is a torque due to our forces, will be equal to our normal minus our mg, and we can simply substitute the values. So we get our torque due to our forces will be equal to, we have this as NL cos of theta minus mgl cos of theta. And from here we can write the equation for our normal. So we can say our normal is equal to torque due to the forces plus mgl cos of our theta and multiply by cos of theta upon L. And this, for equilibrium, this torque due to the forces should be equal to the torque that is being produced. Okay. And therefore this is nothing but our tau, and we simply substitute the values for our tau. So we get our normal is equal to, and this is our mr square omega square tangent of theta, mr square omega square tangent of theta, and 3/2 cos square theta plus 1/4 sin square theta, and we have a plus mgl cos of theta, and this whole is being multiplied by cos of theta upon L, and we got the basic equation, and rest is nothing but simple calculations. And we also know the relationship between L and R. Okay, so we are going to use this particular relationship. Tangent of theta is equal to R upon L. So let me write it here. So we have a tangent of our theta is equal to R upon L. So let us substitute it. So we get this as our mr square omega square, and we have this as our R upon L, and this square cancel with R, and inside we are left with 3/2 cos square theta plus 1/4 sin square theta, and this is our mgl cos of theta, and the entire term is multiplied by cos of theta divided by L. Now let us open the bracket and multiply it. So this we get our LMR omega square and multiply by our cos of theta upon L, and this is our 3/2 cos square theta plus 1/4 sin square theta. This comes as plus, we have our mgl cos of theta multiplied by cos of theta upon L. Okay. And this L and LL cancels out. So From here we can write this will be equal to our, we have our mg cos squared theta plus, and this is left with only mr omega square, and inside we get 3/2 cos cube theta plus 1/4 cos of theta and sine squared theta. So this is our nothing but a normal. It's the required solution for the given question. So this question was a little bit lengthy, otherwise it is quite easy, and for this we have to take care mainly about the directions, okay, because in this figure also we can see there are multiple components, and these components we can easily draw, but we have to keep track of every component. Rest is quite simple. So this completes all the 3 questions. Thank you.